Hey guys, I've set up just a quick sweep here. We've got 30 seconds as the start sweep time, 30 seconds return sweep time. So we have a triangular sweep going on. The frequency, start frequency is 30 kilohertz, stop frequency is 90 kilohertz. So what we're doing is we're using channel 1 on the output to drive our coil through a sweep, and it's a sine wave sweep. It's not a triangular wave sweep, it's just a sine wave. We're on sine at the top there, you can see that. So what we're doing is we're finding the coil resonance by doing this sweep. Okay, now I know where it is, so I can narrow the bandwidth. The bandwidth being 30 kilohertz to 90 kilohertz. I know that the frequency is in the middle of the two figures, roughly. So by narrowing the bandwidth, we can make it easier to show in this video. Okay, now sometimes in some coils the frequency, the resonant frequency, could be hundreds of kilohertz, 600 kilohertz, 1000 kilohertz or more. So the reason I'm showing you this video, the reason I'm doing this video, is to basically show that the coils themselves have a resonant frequency, and that at that resonant frequency the inductive capacitance, which is leading, and then the inductive reactance, which is leading or lagging. So you have inductive capacitance that starts first on low frequencies, and then inductive reactance, which then takes over, becomes more predominant at higher frequencies. So at the resonant frequency, at the main resonant frequency, the inductive reactance is equal to the capacitive reactance. Okay, so the effective impedance of the coil becomes just the DC resistance. Outside those frequencies, whichever is leading, the impedance must include factors of the inductive reactance and stuff like that. It's a little bit complex, but basically what the coil is doing is the coil is allowing for a maximum transfer of energy, if you like, from one terminal to the next terminal at a particular frequency with no real major resistance. Okay, so you can see we're heading up the sweep now. So the sweep will peak at exactly half of the difference, so between 30 and 90, and obviously that is the triangle wave that we saw before, and then it will keep going and then come back down again. Okay, so this is a peak, this is a sweep that lasts over 30 seconds, 30 seconds up, 30 seconds back again. Okay, what we're looking at here is we're looking at the voltage, the terminal, and I think this is really important to state, the terminal voltage on the coil. Okay, so this is the difference in potential. Remember, potential is the charge, the Coulomb charge on the conductor itself. Okay, so how much charge is on the end of the conductor. Now you can see that most of the time the amplitude is reasonably small. Okay, so through the sweep the amplitude doesn't vary a great deal until it gets to a certain point. You can see it's starting to grow there, and then it shrinks back down again. Now this is the inductive reactance, capacitive reactance, and all that sort of thing that we were talking about before. So at the resonant frequency we get a maximum amplitude, and the maximum amplitude is the maximum voltage, and at just there, at the maximum voltage, when it's maximum, is the point where the inductive reactance and the capacitive reactance cancel out. So there's a graph that I'll show that shows the inductive reactance on a plot versus the capacitive reactance. Capacitive reactance is normally the curved line. Inductive reactance is normally the linear line, which is interesting. It's interesting you see them as two different sort of chalk and cheese, if you like, yin yang. You think that they'll both be linear, but they're not linear. One is, one isn't. Now I just want to point out on this note that there's a phenomena that you'll see quite often with coils, and this is something I brought up many times before. There always seems to be a positive number and a negative number. Now, inductive reactance and capacitive reactance cancel each other out at resonance. So if you think about that for a minute, then capacitive reactance will be a negative number and inductive reactance will be a positive number, if memory serves. So 1 plus negative 1 equals 0, and this is the famous equation that I've, a million times, you'll see it on the website a million times. So I want to point this out because this is a common thing that you see with coils. Common thing is one will be a negative number, one will be a positive number. Seems to be a common thing through magnetics throughout. It's something that you'll see on a regular basis. So a positive number plus a negative number, the difference, 1 plus negative 1 equals 0. So it's not a case of just simple addition. Sometimes you've got to think about, and look, science writes off the negative sign most of the time, but unfortunately the negative sign is super important, and it's got to be understood and got to be incorporated into what we're doing, because it's the other half of science. It's the half of science that science is currently missing. Anyway, this video is about coil resonance. This video is about the voltage on the terminals of the coil. So at resonance, you can see it peaks right up there. So we're getting, it's almost double the voltage at resonance. Now outside of resonance, we still see a signal there, but the signal's not as strong. There's more factor in there that's limiting the signal, if you like. So less current will flow, the circuit itself will be interrupted more easy. So there's lots of factors. Now with this technology is not just one coil, and that's why I've tried to share partner output coils from day one. This technology is two coils incorporated into one coil to bring about two different effects in the coil. Now we've seen the resonance before in an earlier video, and the resonance when the coils oppose is what we're looking for. This is the important thing, something I've tried to share from the early days. We need maximum voltage, we need as much voltage as we get. Now voltage is free, voltage is the free component, the current's not. So you can step up voltage with almost no cost at all in a transformer, but you pay the price on the current. Okay, so current is the thing that gets you. Now the Mr. Prever experiment shows how we can amplify current. Now if we can amplify current, if we can take 1 unit of current, and at resonance, if we can turn that 1 unit of current into 2 units of current, which can be done quite easily. We can show in the Mr. Prever experiment that we can get up to about 2 times the current quite easily. And if we can take that fact that amplifying current is a given and we know how to do it, then by increasing the voltage and using Ohm's law, so current I equals voltage V over resistance R. The resistance doesn't change because first of all we're in resonance and we're not changing anything in the load or anything like that. But if we can increase the voltage, then the current goes up for free because we're not paying for the current. The current is amplified in the machine itself with techniques that we know how to do because we've done the Mr. Prever experiment. So it's important to get these coils magnetic fields opposing. Okay, and this is the big red arrows that you see in the partnered output coil image. So we need magnetic fields opposing, we need the coils in resonance, and there has to be semi-loose coupling to make this work. The resonance gives us the voltage, and we can increase the voltage quite easily. There's lots and lots and lots of different ways that we can increase the voltage. But the trick obviously is to amplify the current. These two coils are my partnered output coils. I've got the windings so that this one goes over this way, coming down the former this way to here. Okay, so you can see it's coming up this way to this coil here, to this terminal. On this side it's opposite, so it's wound over the top like this, moving up that way, so that the last terminal's coming up like this. So these two terminals here match, if you like, but they match direction, but the coil itself is opposing. Now if you're in the middle, this all depends on viewpoint, but if you're in the middle, then one will be clockwise, one counterclockwise, depending on which way they're wound. Okay, so winding them down the former or up the former makes a difference. For information on that, go and see my some coils buck and some coils don't thread, because that sort of explains a lot of it. Anyway, what I want to do is I want to point out very simple, very basic phenomena that a lot of people probably have completely overlooked and not even realized the foundation behind it. On this coil here, into this wire here, I've got the positive side of a probe. On this side I've got the opposite. Okay, so if we use the right hand grip rule, positive side of the probe coming in here, we've got a right hand grip rule which would be in under like that, with the north pole out this end. This side here is the opposite, so it goes over the top like this, comes back up on this side, so right hand grip rule that way. Okay, positive side of the probe over here. Each end of the coil has a oscilloscope probe on it, so one here and one here. Now a lot of the time when you're driving a coil or coils like this, there'll be a phase relationship that will tend to try and match the phase of the coils. This is the only way that I've found to wind coils like this, where you can manipulate that phase relationship without getting in too much trouble with your equipment and stuff like that. Okay, now I've got the frequency on both channels, so channel 1 and channel 2 set to 67,500. And what I've done on both channels is I've lined the phase up so that it sort of pretty well matches. You can see there it's pretty close, it's not spot on, it's pretty close. Now what I want to show is a very important wave phenomena that we see in nature that is very easy replicatable here with the setup that I've shown you. Now if we adjust to now what I'm doing, as I just explained before I do it, on channel 2, which is the blue probe, on channel 2 I'm adjusting the frequency up only 57501. Okay, so sorry, 67, so 67 kilohertz, 500, and then 1. So I'm going to go up 1, and you'll see the waveform will start to do some pretty funky things. Okay, so the peak of the wave is maximum when we're 180 degrees. Now that is a little bit abnormal in the fact that you would normally see a reduction in voltage amplitude when there's opposition. But what we're doing in this experiment is we're seeing an opposite to what science would normally tell us. So when we see 180 degrees from the peak of the yellow wave to the blue wave, so about there is 180 degrees out of phase, we get maximum amplitude, which is a very interesting phenomena. The phenomena you might see at the beach, and there's a video that I've played before which I'll show you now.
Dramatic, isn't it? Very dramatic. Wow. Wow. Like symphony.
Which you can actually see the exact same phenomena happening on the beach. Now if I speed it up a little bit, if I go 502, this whole process will go faster. Okay, so a little bit faster again, and if we slowly speed it up, next thing you know, we end up with the same basic waveform that I've shown in my last video. Okay, so we'll get to a point where you can sort of see what's sort of going on, where it's fast enough that you can sort of see the wave structure. And there you go, that's probably fast enough there. So what we can see is that the peak of the wave here and the peak of the wave up here is due to the standing wave of this wave in regards to the blue wave. So the blue wave, if you like, is pumping, which is the difference in amplitude from here to here. Okay, so from there to there, so the difference in amplitude is being pumped, if you like, by the difference of the blue wave. The blue wave itself is causing the rise and decay in amplitude on the yellow wave. Okay, and you can see we're 180 degrees out of phase, so from peak to peak on the yellow, approximately in the middle, is 180 degrees, so 360 divided by 2 is 180, and that's where the blue wave is sitting. So what I really want to show here is how the opposition, and when I say opposition, you can verify that with the right hand grip rule, the opposition of magnetic fields changing in time, interacting with its neighbor's magnetic field, creates this phenomenon. Okay, most people that replicate part net output coils completely forget about the right hand grip rule and the magnetic fields opposing and all that sort of thing, and this is the critical part. This is the part that needs to be investigated. This is the part that in every single electrical generator we see energy being pumped as a result of equal and opposite magnetic fields. Okay, Faraday's law of electromagnetic induction, negative d phi dt. Alright, so I just want to show you this, and I just want to go into a little bit more detail. Floyd Sweet was an absolute genius. I wish I'd met the guy. I never did, and I never got to examine his vacuum tried amplifier. It would have been great, but unfortunately, from a standpoint of if I had, then maybe this wouldn't have been so difficult and such a challenge to solve this riddle. Anyway, Floyd Sweet's papers, all of them are worth a very, very close study. Floyd Sweet's knowledge was unbelievably advanced, so I do believe he had much higher training than what some people would like to have others believe. Most forums don't touch on the electrical generator or most parts of induction full stop, which is a real shame, because obviously that's where nearly every single inventor through history has touched, including Floyd Sweet. For example, Clemente Figura said in studying the dynamo, in one of his papers, that was one of the opening sentences. I think it's very important to know basic electromagnetic induction rules. Without them, you may as well give up. If you're not prepared to study electromagnetic induction and get a good grasp on it, then you really are wasting your time. This is a small snippet from the paper, and I've highlighted some points here. So this is the only part that really talks about the construction of the vacuum triode amplifier, and you can run through and read it, but basically I just want to point out there's certain key words here. So things like inwardly directed, things like current and magnetic field follow the right hand grip rule. No grip in there, but right hand rule, people know what I'm talking about. Things like one of them is moving up while the other one is moving down. Okay, so we're talking about different velocities, different directions. Well, the velocity will be the same as a matter of fact, but the direction will be different. Okay, so we're talking about one bifilar element, current and the right hand rule in one direction moving up, and one bifilar element moving down, current and the magnetic field follow the right hand grip rule. Okay, so remember the electric field and the magnetic field are at 90 degrees to each other, so one vertical to both. Okay, vertical would be obviously 90 degrees to the magnetic field. So Floyd Sweet's interpretation here, how he's telling you to build the machine here, is 100% correct, and that is the basis, the very basis of partnered output coils.